In this video we're going to go over the Chatelier's principle, which is something that allows us to predict how a system at equilibrium will respond to any changes. So the Chatelier's principle says that if a change occurs in the system at equilibrium, then the equilibrium position will shift so that the system can act to reduce that change. So the most common type of change is a change in concentration or partial pressure, which happens when we either add or remove a component. So the equilibrium, if a component is added, it will shift so that the component that was added gets reduced. So let's look at an example. So we have this reaction here, and we want to predict how the equilibrium will shift. So the first type of change is the addition of carbon monoxide. So when we add more carbon monoxide, the concentration of carbon monoxide increases so that the system is no longer at equilibrium. So in order to re-establish equilibrium, the system will shift to the left so that the concentration of carbon monoxide is reduced, and so will the concentration of As4. So the system will consume carbon dioxide and arsenic to produce these reactants until the equilibrium is re-established. So here are the concentration changes of each component. Both products will decrease in concentration since the equilibrium is shifting to the left, while both reactants, since they're solids, their concentrations don't change. Even though more of them are being created, their concentrations remain constant. If we add tetraarsenic hexoxide, this is a pure solid, and since pure solids have no effect on the equilibrium position, no shift will occur. This is because even if we add more of this, the concentration will remain the same, since it's a solid. If we remove arsenic, then in response to this decrease in concentration of arsenic, the equilibrium will shift to the right to make up for the lost arsenic. So it will consume the reactants in order to produce more arsenic and carbon monoxide until the equilibrium is re-established. So again, the solids stay at a constant concentration, and here, since it's shifting to the right, the concentrations of both products increase. Next, we're going to be looking at pressure changes. We already looked at one type of pressure change, which is just adding or removing a component in order to change its partial pressure. Another way to change the pressure of a system is to add an inert gas, and inert just means that it does not react. So when you add an inert gas, it increases the total pressure of the whole system, but since the gas does not react, then there is no actual effect on the concentrations or partial pressures of the reactants and products. So when we add an inert gas, the equilibrium does not change. Another way to change the pressure of a system is to change the volume of a container that is holding a gaseous system at equilibrium. So when the volume is changed, the system will respond by changing the number of gas molecules in order to change its own volume and fit the new container. So if the container volume increases, the equilibrium shifts to the side with more gas molecules, because it wants to increase the total gas molecules in order to fill up the more space that is created. If the volume decreases, then the system will shift to the side with less gas molecules, causing the system as a whole to shrink in order to fit the smaller container. So if we have this reaction, there are two gas molecules on the reactant side and only one gas molecule on the product side. So when the volume of the container is reduced, the equilibrium will shift to the side with less gas molecules, which is the product side. So it will shift to the right in order to fit the smaller container. Because the volume of a gas is proportional to the number of moles. So if there are less total moles in the system, then the volume will also be less. If we have this reaction, there are 4 gas molecules on both sides. So if we reduce or increase the volume of the container, the equilibrium will remain unchanged since both sides have the same number of gas molecules. So neither side is more favorable than the other. The last type of change we're going to look at is temperature changes. Now, changes in temperature are different from concentration or pressure changes because when we change the temperature, we also change the equilibrium constant as well as the equilibrium position. So, in order to predict the shift, we have to treat energy as either a reactant or product, depending on if the reaction is endothermic or exothermic. So if we have this reaction with a positive delta H, remember a positive delta H means the reaction is endothermic. It takes in heat. So we can treat energy as a reactant, like this. And then from here, we just use Le Chatelier's principle to determine the shift when the temperature changes. So we want to know how the equilibrium will react when we increase the temperature. So if we increase the temperature, we can pretend like the energy's concentration is increasing. So the reaction will shift to the right. And since it shifts to the right, that means more products are being created, while more reactants are being used up. So since there are more products, the value of K increases. Since remember, on the numerator of the equilibrium expression is the product concentrations, while the denominator is the reactant concentrations. If we have this reaction with a negative delta H, this reaction is exothermic, which means it releases energy. So we treat energy as a product. So here, if the temperature increases, then the energy will increase, and according to Le Chatelier's principle, the equilibrium will shift to the left. And since it shifts to the left, that means the concentrations of the products are decreasing and the concentration of the reactants are increasing. So the value of the equilibrium constant, K, will decrease as the temperature increases.